Okay, so I think we'll get started. I don't want to delay this longer because I need to run to the train station a little bit early today to catch a 3 o'clock train. So we're going to have an intense lecture. Okay, so we're hopefully going to finish memory interference and quality of service. This is the third lecture on this. It's an important topic. And then we're going to start multi-core cache management, which is essentially very similar topics, but their efficiency is also very important there. So before we get started, I'll remind you again, this very fine gentleman, he's going to visit us, give a talk. So please attend, ask questions about data flow. So he'll like it, I think. You will like it too. Okay, so this is what we were doing. We basically covered prioritization or request scheduling and data mapping, two fundamental techniques to reduce interference and provide quality of service. Now we're going to jump to the next two. We're not going to put as much emphasis on these three as compared to the prioritization, but these are also very, very important. And in fact, combination of these mechanisms really provide the best interference reduction, as we will discuss in a little bit. Okay, so coarse source throttling. What is the idea over here? I gave you the idea actually. If you remember, I drew a picture of a cloud over here and then shared resources. You have sources that are injecting into the cloud. That's the idea over here. Throttle the sources as opposed to changing the resources internally. So we have many shared resources, as you can see, and you really want to control interference on all of these shared resources. A very powerful technique is to handle this interference at the sources over here by throttling the sources. Saying if a core is basically denying service to another core, if you somehow figure it out, and then throttle that core such that it doesn't inject as frequently into the shared resources. It's very powerful because now you can actually control access to all of the shared cloud, if you will, all of the shared resources over here. Okay, so basically, what is the problem with smart resources? The alternative is having smart cache, smart memory controller, smart DRAM, which basically handles interference and provides quality of service in a configurable, controllable way. The problem is that you can actually design these mechanisms into caches, into interconnect, into memory, but they can contradict each other. And this paper actually shows that they contradict each other. If you have a cache partitioning mechanism, and then you have a memory scheduling mechanism, let's say PAR-BS, and a fair cache partitioning mechanism, these do not necessarily coordinate well with each other. You partition the cache, one application has a lot of requests into the memory, and that denies service to some other application. So you need to somehow coordinate the mechanisms that you put into caches and memory controllers, and that requires complex implementation. So one of the questions that was asked was, how do we enable fair sharing of the entire memory system by controlling interference in a coordinated manner across all of the resources? And source throttling is a good substrate for something like this, because sources are the things that are injecting into the resources, if you will. You can have complete control in the boundary of injection. Okay, the key idea is very simple. Manage inter-thread interference at the cores or sources, not at the shared resources. Of course, as we know, this is not black and white. You could have a combination of both also, but we're going to treat it as not a combination at this point. So what do? One mechanism could dynamically estimate the unfairness in the memory system by using some counters and feedback this information into a controller. That controller could be centralized, let's say. And that controller throttles cores memory access rates accordingly to satisfy some target. Basically, whom to throttle and by how much to throttle depends on the performance target. If you're maximizing throughput, for example, you may want to throttle back workloads that are very memory intensive, that are denying service to others, right? If you're maximizing fairness, then you may want to do something else. If you're maximizing per thread quality of service, maybe estimate the slowdowns of different threads and do the throttling such that you achieve some particular slowdown bound for the different threads. Make sense? Yeah. So it's a very powerful mechanism. It's employed in the internet, for example, right? You do congestion control in the internet. You throttle the sources in TCP/IP, for example, and you do exponential backoff, for example. There are many, many algorithms for it. So it's not specific to clearly the memory system. For example, if the unfairness is greater than some system software specified target, then you can throttle down the core that's causing the unfairness and throttle up the core that was unfairly treated. Of course, to be able to do that, you need to add a lot of counters into the system to figure out the unfairness, to figure out who's causing the unfairness, and to figure out who should be prioritized, right? And you could do this in many ways. You could do this using heuristics, for example. You could do this using slowdown estimation techniques that we discussed. Those could be, actually slowdown estimation techniques are a good way of driving these mechanisms that can do throttling. Actually, this paper proposes this slowdown estimation technique, but you could do it with other heuristics as well. And this is the paper that first introduced the idea within the context of the multi-core memory system to manage caches, main memory, and interconnect at the same time. And this uses, as we discussed yesterday, a slowdown estimation mechanism that's relatively similar to stall time fair memory scheduling, but it's actually more advanced because it uses also caches. It takes into account also caches. I'm not going to go into the details of the slowdown estimation mechanism. You know the basics. Actually, you have a better mechanism now. You know of a better mechanism now than what this paper proposed. Okay, so if you want to do this, let's take a look at how an example thing works. You have two components. You're again interval based. You divide time into intervals. During an interval, you evaluate the unfairness during runtime in hardware. Basically, you dynamically estimate the unfairness, application slowdowns in the memory system, estimate which application is slowing down which other one. So you need to add additional counters to say, oh, this application is causing this much interference to this other application. So that's what this paper proposes. If you really want to figure out whom to throttle, you need to have some information about who is the bad core, basically. You want to distinguish the bad cores from the good cores with some definition of bad or good. And it's not easy, as you can see. This is going to add a lot of counters into the system. So even though resources are not smart in the sense that they are not providing control and configurability for interference, you still need to add some counters to keep track of what's going on in the system. So that's going to be the downside of these mechanisms. You need to have some information. How do you collect that information? And if you really want to be accurate in what you're doing, that's a lot of information potentially, because if you think about, let's say you have 1,000 cores that are sharing the memory system, essentially you have a 1,000 by 1,000 matrix that says, oh, this core is causing this much interference to this other core. Of course, this is the worst case, perhaps. Maybe you don't want that fine-grained information, but if you have that fine-grained information, you can probably make some decisions. Okay, let's assume that you've done this with some mechanism. Then you feed that information to a controller, and the controller employs dynamic request throttling. This could be done in hardware or software, assuming software has proper fine-grained access to the request throttling engines, and I'll discuss a little bit. Basically, this dynamic request throttling adjusts how aggressively each core makes requests to the shared resources. For example, it could throttle down request rates of cores that are causing unfairness. How would it do that? It could, for example, limit the number of cache misses that these cores may have outstanding. A bad core, bad behaving core may have outstanding, right? Or it could limit the injection rate. You could say you cannot inject one request. You cannot inject more than one request every, 100 cycles or so. So you need to have thresholds to be able to adjust these. And actually, that's another downside of these mechanisms. It's very powerful, but now you need to be able to adjust the thresholds. And how to determine the thresholds actually is really the Achilles heel of almost all of these source throttling mechanisms that are employed in systems. That's true for the internet also. How do you determine the thresholds to decide, first of all, when to start throttling a source? And how do you determine how much to throttle that source, right? How much do you back off, right? And if you back off too much, you limit your throughput in the entire system. If you back off too little, you may not be solving the problem that you're trying to solve, which is ensuring that this core doesn't deny service to some other core, right? So that's the downside of these mechanisms. They're based on thresholds, and it's not clear if there's any other way of designing them without these thresholds. And it's very difficult to determine these thresholds. As you will see, there are many thresholds in this mechanism. Okay, so this is the pictorial view of fairness via source throttling, one example of this. You have this runtime unfairness evaluation engine. During an interval, you do slowdown estimation for all of the cores using your favorite technique, if you will. This paper has a not so accurate technique, but that's okay. It works well overall because you don't need to exact slowdowns for some of the things that you want to do. And then you estimate system unfairness at the end of the interval. You find the application with the highest slowdown, application slowest, let's call it, and you find the application that's causing most interference for the application that's slowed down the most. Let's call this application interfering, or the bad app. And you feed this information to the dynamic request throttling engine at the end of the interval. And the dynamic request throttling engine takes some action. For example, if the goal is to ensure that unfairness doesn't go above some amount, it compares the unfairness estimate that's provided during this interval to some target, let's say system software specified target. And if the unfairness, estimated unfairness is greater than the goal, then you throttle down the application that's causing a lot of interference, and you throttle by limiting its injection rate and its parallelism, and you throttle up that application that has been slowed down the most. This is one way of doing it, of course, right? You may decide to throttle down multiple applications and throttle up multiple applications. Now you see that there is more complexity in the system, right? It may be actually even more complex than doing memory scheduling at the memory controller only, because there are many, many design choices here. Okay, so basically how do you, yeah, that's how it works. And this could be configurable. This target could be, I don't know, if the application that you really care about is not meeting its slowdown bound, for example, then you do something about it. So it's very flexible in terms of what you can specify. So let's talk about dynamic request throttling a little bit, just to get some insight into this mechanism. Hopefully you see the complexity in terms of understanding what's going on, but also throttling aspect is complex as well. We want to adjust how aggressively each core makes requests to the shared memory system. And there are two mechanisms that are proposed in this work. You basically have a quota on miss status holding registers, miss buffers. You control the number of concurrent requests accessing shared resources from each application. You say you can only use one miss buffer, have one outstanding miss. Clearly this is not good for the performance of the core that's executing the application, right? Because maybe the application has a lot of memory level parallelism. You're limiting the memory level parallelism of the application. Or you can limit the request injection frequency. You can control how often memory requests are issued to the last level cache from the miss status holding registers, miss buffers. And again, you're limiting the parallelism of the application as well as latency, like how often. And if you actually limit this a lot, then the application is not making progress, right? Okay, so this is one example of how complicated this could be. This is what we came up with. These are the different throttling levels of different cores. And we assigned different throttling levels to each core. It determines both the MSHR quota and request injection rate. As you can see, I don't know, it's very hard to say these are the best options, clearly. These are things that we just thought were good. But you see that these thresholds come in the way at some point. How do you know that this is the right way? And also there's a transition between the thresholds. If you're at 100%, and if you figure out this core is doing bad things to some other core, where do you transition next? Do you go to 50% and then you incrementally go this way? Or do you go from 100% to 2%? It may depend on how badly this core is interfering with another. But there are many, many design choices here. I call this many, many moving parts in a mechanism. It's a very good idea, but implementation, at the implementation level, you need to be very, very careful to get this to work. It's not easy. But this paper actually shows that it works nicely, but it may be brittle when you actually combine it with many techniques. Okay, whenever you have many, many thresholds, the techniques become very brittle in general. We talked about TCM, for example, thread cluster memory scheduling. It's very similar. It's a brittle memory scheduling technique because it actually has multiple thresholds, but this is much more, as you can see. And this is just the throttling level. There's also determining whom to throttle. Okay, so there's also, but this sort of techniques is good because they actually enable a lot of flexibility. For example, you can fix different fairness objectives. You can configure, system software can configure them. As I said, you can keep the maximum slowdown in check. You can try to throttle things such that the estimated maximum slowdown is less than the target maximum slowdown. Of course, that may require good slowdown estimates, as we discussed. Or you could keep the slowdown of particular applications in check to achieve a particular performance target. The estimated slowdown of an application should be less than some target slowdown of an application. And there's support for thread priorities. You can actually weight the slowdown that you compute by some weight that is assigned to the application by the software, by the system software. And you can see the evaluations of these in the paper. Okay, any questions? I've given you the basic concepts. So I'll give you the results, not in detail, but I'll give you the takeaways from the results. You can read the paper again. This is one of the potential papers that you can pick to review, but you can always review any paper if you want. You don't have to have a homework for that. Okay, so the source throttling alone actually provides better performance than a combination of smart memory scheduling and fair caching. That's what the paper shows. The paper shows if you take a smart memory scheduler, PAR-BS actually, and a caching cache partitioner, and if you combine them, they improve performance. Sometimes they actually reduce performance if you combine them, because decisions that made at the memory scheduler and the cache sometimes contradict each other. But if you do source throttling, it's a more coordinated technique. It really considers all of the resources, assuming you added the counters to consider all of the resources. So source throttling alone is actually better than these techniques in the paper. But it turns out neither source throttling alone nor these smart resources alone provides the best performance. So sometimes having a smart memory scheduler plus a fair cache provides better performance than source throttling by itself. So it's not, there's no single best mechanism that's dumb resources versus smart resources implemented in these ways. There's no single best mechanism. So combined approaches are even more powerful actually, source throttling as well as resource-based interference control. And this is what's happening in the internet, for example. In the routers you have some control in terms of quality of service, and in the sources you have some control in terms of backing off, source throttling, and you need to somehow coordinate them, but it's not clear if the internet is the best way to coordinate resource control mechanisms. Whereas in a multi-core system you have a lot more control because you know you're in a single chip, right? Okay, let me talk about the advantage and disadvantage of this. I think most of them are clear by now, but it's actually easy to implement from one perspective, which is there's no need to change the memory scheduling algorithm, there's no need to change the cache, there's no need to change your interconnect. From that perspective, this is easy to implement. If you look at the basic idea, you throttle the sources, right? That's it. It can be a general way of handling shared resource contention, much more general than doing a memory scheduling algorithm, because memory scheduling algorithm is not enough. This controls many, many resources. And it can reduce the overall load and contention in the memory system. Basically, this enables you to get to a point where you're not oversubscribing the resources. Maybe this is a good time to show this load latency curve again. Do you remember the load latency curve? Yes? No? Well, I'll remind you. Do we need to change the lights? Light. Lecture. That looks better. Maybe. Okay, basically load latency curve. We're going to see this again in the interconnects. It's very fundamental to pretty much everything, but this is the load. And this is the latencies that you see. It could be average request latency, for example, or maximum request latency. It doesn't matter. And load is essentially how many requests you're injection, or this is also called injection rate sometimes. There may be multiple ways of defining this axis, but how many requests you're injecting per cycle on average. And usually this curve looks like this. Basically, you have some amount of so if you're not very heavily loaded, you have some minimum latency in the system, assuming some access pattern. Usually you assume an access pattern. And if you actually keep increasing the load in the system, if you keep injecting, your latencies start increasing slowly. And after some point, you've injected so much into the system that there's so much congestion. And at that point, essentially your latencies shoot up. So this area is an asymptote. This curve goes to an asymptote, and this is usually called the saturation throughput, T-put, let's say. So basically here the system, the shared resources are saturated, and this is clearly called the minimum latency over here, or zero load latency over here. This is the latency that the system has if you have zero load. There's no other request in the system, one request goes that way, and that's the zero load over here. So if you have a system that's too overloaded, you may be operating somewhere over here basically, which is not good. You overloaded the system, right? Your latencies are too large, and you may not want that. There's a lot of congestion in the system. So if you throttle the sources, what you're doing essentially is you're moving your operating point from here to here. So you may be operating over here, which is a much more comfortable place to operate at. Now your latencies are much lower. So that's the idea of source throttling, explained in a different way if you will. And we're going to see this a lot more in the interconnect lecture. And we're going to actually see what affects these latencies over here and what affects your throughput over here. For example, one thing that really affects your latencies is clearly how many banks you have in the system, how much memory bandwidth you have in the system. Those will affect your minimum latency. Those will affect your saturation throughput. How many memory channels you have definitely affects the shape of this curve. Let's say this curve is for one channel, one memory channel. Maybe if you have 2 memory channels, I'm just going to give you a basic change. It looks like this, right? For the 2 channels, because you have more bandwidth that you've added to the system, you'll saturate much further. Now, if you have more channels, I don't know, 16 channels, the curve may look like this. Make sense? So basically, by adding more bandwidth to the system, you're changing the curve, you're shifting the curve, and you're actually moving your reasonable operating point to the right. And if you somehow still saturate your system, for whatever reason, you're operating over here, you can use source throttling to move your operating point to a reasonable point, whichever curve you're on. Okay, so that's the idea of source throttling, basically. Which means that you're reducing the overall load and contention in the system, and that's enabling you to operate at a much better point. Okay? You cannot do this with memory scheduling. And you can do this with mapping, data mapping. You basically partition things, but you cannot do that as well because you're really moving from some point to some other point, and those points are probably close to each other. But the source throttling is a very powerful way of actually doing this. Okay, so let's talk about disadvantages. We talked about the advantages. Well, we said that it requires slowdown estimations, or at least some way of figuring out which core is causing interference. Depending on how you would like to use this information, you need to have some way of figuring out what is the interference impact of core I on core J. And that could be difficult to estimate. That requires a lot of counters. And we already know slowdown estimations are difficult to estimate, but we have some mechanisms. Thresholds can be difficult to optimize. This is actually perhaps the biggest disadvantage. How do you optimize those thresholds? I don't know. This is actually a very hard thing, because this is not just one single threshold. This is not 2 thresholds, not 3, not 4, not 5. This is maybe 50 thresholds to optimize, actually. And I don't know if there's a good way of doing it. I don't think even the machine learning hype can fix this problem. Maybe it can. It's good to think about this. So if I believe machine learning can do one thing, is enabling such techniques by making these thresholds very easy to optimize. But this is a very multi-dimensional surface and curve, so it's very difficult, I think, to optimize these thresholds. I think certainly for humans, but it's not clear for machines it'll be easier because, yeah, maybe with humongous amounts of data you can, but I don't know. So basically, if you don't optimize your thresholds well, what is the downside? Basically, you can lose throughput because you do too much throttling. That's one downside. But the other downside could be you may not actually solve your problem. But of course, if you're not solving the problem, if you're not satisfying the target, then you probably can figure it out and you try to optimize your thresholds. But it takes a long time to converge potentially, and it's not clear if you converge to your target in this case. So it seems like a good fit for studying this for machine learning, actually, using some machine learning techniques, but it's not clear it'll be easy. Basically, it can be difficult to find an overall good configuration for source throttling. And okay, and this paper, if you read it, hopefully you will see a lot of the aspects of what I discussed. Any questions? Comments? No? Okay, so source throttling is actually employed in many places, internet of course, but we're not talking about the internet. We're going to talk about on-chip interconnects in a little bit, and there's a lot more interesting stuff to do in on-chip interconnects, and these are some of the works that we've done in the area. This, for example, looks at the differences between on-chip networks and internet scale networks, and how to do throttling, for example. It's very interesting. But I'm not going to talk about it right now. If we have time, we can talk about it when we talk about the interconnect lectures. Okay, so we've covered the third one also. Now let's talk about the last one. This is the last fundamental technique to control interference. And this is basically, this application or thread scheduling enables us to put applications that interfere with each other far away from each other. Basically, pick threads that do not badly interfere with each other to be scheduled together on cores that are sharing the memory system. Hopefully this is also obvious, but how do you do that is not easy. So there are several works in this area. I'm not going to go through all of them, but I'm going to give you one example over here that actually, I'm going to go through this quickly, that actually considers a network also. Because I think in this case you really need to consider the topology of the system. So you have multi-core, you move to many-core, you have this stuff. And there's on-chip communication. So you have, let's say, this application over here, and you have many memory controllers. This application can require access. So these are 4 different memory channels over here. They're controlling 4 different memories, partitioned. And this application, also cache is partitioned. Cache is actually distributed across the chip. This is one way of scaling the system up. So you can have a shared cache bank here. You can have all of these tiles have shared cache banks. I think this is 8 by 8, right? I didn't count it, but it looks like a 64 core system. So if this application is mapped here, and if it needs to access a cache, let's say, it sends a request to access the data at that cache. So there's a mapping function between the address and the cache bank. So you need to figure out that mapping function and route the request. And if the cache is a hit, then provides the data. Right? That's good. But what if it is a cache miss? Then the application sends a request. Cache says it's a cache miss. So cache sends a request to the memory controller. And the memory controller satisfies the request and then sends the data back to the cache. And the cache sends the data back to the core that requested it. So that's one way of doing communication between the cores and memory in a distributed on-chip system. And this is distributed because you have all cores in all of these 64 tiles, and you have some network that connects them, which is not shown here. It's not that important. It could be a mesh network, for example. And there's some sort of routing that you do, as you can see. We'll see all of this when we talk about interconnects, XY routing in this case. So what happens if you have some other application that over here that interferes with this application? Let's assume this is light meaning compute intensive, and this is heavy meaning memory intensive. This heavy application can actually deny service to this light application. While this light application is trying to access this memory controller over here, this heavy application can send many requests to the memory controller over here. As a result, it can interfere with this light application. So if you know the characteristics of the applications, maybe you can do some things at the system software and hardware software cooperative layer such that you schedule these applications such that they do not interfere with each other. Right? That's the idea over here. Then the question is, what are the levers that you have to do that sort of scheduling? So for example, you could say this application is going to access only these memory channels. So you could do memory channel partitioning, which is going to be part of the ideas as we will see. It's a very powerful idea. It's called clustering over here. So you could say basically this application, the applications that are mapped over here can access only this memory channel. The applications that are mapped over here can access only this memory channel. And you could partition the network into quadrants. And this actually needs to be done if you want to isolate things. Okay, basically you have a spatial task scheduling problem. You have these applications and you want to map them to the cores. How do you map the applications to the cores? And how do you map the applications to the memory controllers as well? So there are many questions over here. I'm going to talk about several, but these are not comprehensive. How do you reduce the communication distance for an application? Because if an application is mapped over here, does it make sense for it to go over here to the memory controller? Maybe not. How do you reduce destructive interference between applications? What we've been trying to do so far. We're going to try to do it in different ways. And how do you prioritize applications to improve overall throughput? And I'll give you several ideas that are in this work. These are very fundamental ideas, some of which we've already discussed. So let's take a look at the first one. The first one is clustering. Basically, this picture shows the ideas in a pictorial way. Clustering means cluster the applications to the memory controllers. So it's essentially memory channel partitioning done in a network system that looks like this. And this is going to buy us the biggest benefit, actually. So what this does is basically it puts the applications into quadrants, and it says this application can access the cache banks as well as the memory controllers only in this quadrant. Ditto for the application over here in this quadrant. And if this is light and this is heavy, now they're not interfering with each other. That's great, right? We basically partition the cache banks and we partition the network, we partition the memory channels. So you already know this idea. The next one is how do you improve the bandwidth utilization? So how do you map the applications internally over here? That becomes now tricky. So you want to balance the bandwidth across the quadrants such that no quadrant gets overly loaded. So if this quadrant has only light applications, for example, if this quadrant has only heavy applications, that may not be extremely good, right? Because now there's a lot of bandwidth requirement over here, but this quadrant may not be able to satisfy the bandwidth. Actually, exactly what I showed you happening maybe in this quadrant. It's always good to think about these curves. Let's assume this curve is the curve that we have. If this quadrant is only heavy applications, it may be saturated. Whereas if this quadrant is only light applications, it may be operating at this point. But that's not good for the entire system because you're not really utilizing your resources really well. Okay. So there's the idea of balancing. How do you do that? And then there's isolation. So this is actually important. If you really want to improve overall throughput, you actually need to give up some balance, perhaps. Maybe you really want some light applications that are just mapped together, and you balance the load across these different quadrants somehow. And if you do that, these applications are isolated. Right? So balancing usually goes against isolation. That's the unfortunate part over here. If you want to balance the load, things may look like this. You want to put light applications and heavy applications and medium applications, and you want to have a good balance across these 4 quadrants. But if you want to isolate the performance of some applications, especially the latency sensitive ones, you may not really want to balance. So there's a fine line between balancing and isolation. And again, there's no perfect solution, I think, here. Okay, and then this work also shows, so exactly, that's what this work says. Basically, you do isolation of really latency sensitive applications in one quadrant, and everything else is somehow balanced. And then you do radial mapping. Applications that require a lot of throughput are mapped close to the memory controllers. So you can read the paper for more detail. Actually, this paper does a lot more than that. It introduces a page mapping mechanism that essentially tries to minimize the page faults. Because you have you basically partition the channels right now. How do you do the page allocation such that you minimize the page faults when you have partitioned channels? We didn't discuss that in memory channel partitioning, but you actually need to think about that, even if you're doing soft partitioning. Okay, so step 1, as we've discussed, as opposed to having this application access all across the network, all the shared cache banks, all the shared memory controllers, this is inefficient. Limit its access to the clusters. So that's the idea. You can only access here. You improve the locality, actually, this is good. You may not have all the cache space, but if there are enough applications over here, you may not want a single application to have access to all of the cache space anyway. Right? If you're the only application, maybe you want to have all of the cache space, of course, or have access to all of the memory controllers. And this heavy application now gets mapped over here. As a result, you reduce the interference between the heavy application and the light application. Right? Whenever you isolate, you get actually good interference reduction. So this is the idea of cluster data mapping, or memory channel partitioning, or memory bank partitioning, cache bank partitioning applied to a network system. It's nothing really hugely new here. But it actually shows you how much that buys. So this is baseline over here, and you can read the paper. So these are actually a lot of applications, I think 64. And applications in aggregate have different intensity. So in aggregate, this set of applications have 500 MPKI total, and this one is very intensive, as you can see. So this is the baseline performance, and if you actually do clustering, you get a lot of performance, as you can see over here. On average, you get about close to 10%. And if you do everything else that we've briefly discussed, you get another, I don't know, 7 or 8%. And you can read the paper for more details of these applications. So system performance overall improves by 17%. I'm not going to go through the details, but I gave you the basic insights. If you go through the details, it's going to be very long. So this is another effect, actually, which is really nice, I think. If you do clustering, you're also reducing the communication distance. You're not accessing all 4 memory controllers. You're accessing one memory controller that's close to you. Right? That's true for cache banks. That actually reduces your power in the network significantly. So you can see that clustering actually reduces the power, I don't know, by 15%, or maybe actually, no, this is 30%. And then on top of that, if you do everything else, like balancing, isolation, and then this radial mapping that we discussed, you reduce the network power even more. So if you actually intelligently manage your resources, you not only reduce your interference and improve performance, improve fairness, maybe provide quality of service. This paper doesn't tackle that part. But also you more efficiently utilize your energy and power. So we didn't discuss power in any of the previous works. But if you're more efficient in terms of how you use your resources, you usually improve your power efficiency as well. In this case, it's very significant because it's a huge network system. And network power, as we will see when we talk about interconnects, is a big component of the system power. So it's going to be important to use these techniques to reduce power. Okay, any questions? Okay. So let's look at another example over here at a little bit higher level. The interference over thread scheduling is done actually in many environments. I've just given you a distributed on-chip context over here. But there's also a distributed system context, which is compute clusters essentially, or data centers. And data centers clearly can be running virtual machines or applications. And this is one example over here. Basically, you have some applications that are encapsulated in virtual machines. And the key question that a cluster scheduler needs to answer is, how do you dynamically schedule these virtual machines onto these hosts? There are many considerations over here, but one consideration is a microarchitectural consideration. What happens, which applications should you put on the same host such that you maximize performance and minimize interference between the applications and satisfy quality of service? So this is actually the problem that all of the data center or cluster schedulers have. And these are called distributed resource management policies, and it includes a power management also, but we're not going to talk about the details of it. Usually, these policies are based on operating system level metrics like CPU utilization, memory capacity demand, and you try to bin the applications into the hosts such that you maximize CPU utilization and maximize memory capacity demand, but not oversubscribe either of those. So let's take a look at an example of this. So let's assume that you profile the applications, or somebody tells you this information. This is the CPU utilization of an application, and this is the memory capacity that's required by the application. And you have this information for all of the applications that you want to schedule into your cluster. Now you basically make a choice. You do bin packing, if you will. This is one example, bin packing. These three applications go to this host, and this huge application that requires large capacity and a lot of CPU utilization goes to this host over here. So that's one way of doing it. Now the unfortunate thing over here is this doesn't take into account the interference that's happening between applications, right? If you just look at memory capacity and CPU utilization, that's not good enough, because we know that there's a lot of interference that happens at the DRAM and caches. This doesn't take into account any of that. So basically we have microarchitectural level interference. The applications within a host, I call them applications, but you can call them virtual machines as well. For me, it's the same thing. But it's really, in a virtual machine, you can of course encapsulate many more applications, right? So virtual machines within a host compete for shared cache capacity and shared memory bandwidth and interconnect, as we will see. The key question is, can operating system level metrics capture the microarchitecture level resource interference? And the answer is no, because if you look at CPU utilization, this basically tells what fraction of the time is the application running on the CPU, not doing I/O. It's not waiting for I/O. It doesn't take into account cache misses. It doesn't take into account any other stalls that happen in the pipeline. So it's an operating system level metric. So these applications have very high CPU utilization, and they have very high memory capacity, as you can see over here. And as a result of this, you may want to schedule, actually these are real applications that are in the paper. You may want to schedule two of the red applications together over here and two of the yellow applications over here, because there's no difference between these applications with these metrics. But if you look at the microarchitecture level metric, let's take a look at the last level cache hit rate. It's 2% over here, it's 98% over here for this application. And you guessed that this is a streaming application, as you can see. And the memory bandwidth demand of this is huge compared to the memory bandwidth demand of this other application. So if you just use these metrics to schedule these applications to the different hosts, you will get a schedule like this. but this schedule is pretty bad from an interference perspective because the red applications have a heavy demand on the memory system. So they're basically destroying each other. They're operating at this part of the curve. Whereas these other ones, the yellow ones, do not access memory often, so they're operating at this part of the curve. Right. So basically, you're not utilizing your resources well, and also you're causing a lot of problems probably because these applications are probably getting slowed down a lot, whereas these applications have ample resources that they're not using. So the impact on performance, these are real results from real systems actually. The performance that you get over here is, let's say, this much. That's the IP instructions per cycle. If you actually were aware of this interference, you could do a schedule that looks like this, basically. You swap these. Well, maybe you don't do it via swapping, but whenever you schedule it, you do it in a nice way. In this case, you see that things are more balanced, and you see that you're utilizing your resources in a more balanced manner. Of course, you could have other policies that are more careful in terms of the interference, but we're not going to go into the details of that. But if you look at this, you actually improve your performance significantly by just doing a very simple thing, in the sense that you take into account the microarchitecture level behavior of the different applications, the last level cache hit rate and the memory bandwidth demand. And you input that into the cluster scheduling engine. Okay, so that's the idea basically. I've given you the idea. Then the rest is all implementation. You take into account the microarchitecture level shared resource interference. You monitor it, you detect it, and you balance microarchitecture level resource usage across the cluster to minimize memory interference while maximizing system performance. That could be one goal. Of course, these schedulers have many, many goals. Again, if you have a service level agreement with a particular application, then you want to actually prioritize those applications while doing this as much as possible. So I'm not going to go into this detailed. If you want, you can read the paper that I'm going to reference in a little bit. But this is essentially how a lot of the cluster level schedulers behave today. They have an OS and a hypervisor, and you have a profiler. Usually the profile looks at CPU and memory capacity, but increasingly they're looking at architectural resources as well. And this paper proposes looking at architectural resources. And you profile, you look at the interference, and you basically try to map the applications that do not interfere badly with each other on the same hosts. And you may need to migrate things once in a while, depending on when the applications change their characteristics. And actually, existing systems have sophisticated migration policies to ensure service level agreements to reduce power consumption in the system, but I'm not going to go into that in detail. Okay, so that's another example of reducing interference at a slightly higher level using thread and application level scheduling or virtual machine scheduling. Any questions? Okay, let's talk about the advantages and limitations of this also. Advantages, basically this is thread scheduling in general, not just the virtualized example that I just gave you. If you actually do this, you can minimize and eliminate interference by scheduling symbiotic applications together, as opposed to just managing interference, right? So if the applications are doing well together, then schedule them such that you can eliminate and minimize interference. And this is also less intrusive to hardware. There's less need to modify the hardware resources. Again, here you just need performance counters, right? And mechanisms to be able to map the applications to different cores or different hardware contexts. So you don't need to change. This is a dumb resources approach from that perspective. You don't need your resources to be smart. You just need to monitor them and have information about them. Of course, like everything else, this has disadvantages and limitations. Now you need to actually migrate the threads and data between the cores and the machines, and that takes time, and that's high overhead. If you want to schedule this application from this machine to this other machine because it's going to interfere with some other one, that's basically thread and data migration. One issue with these approaches is you need to have a lot of heterogeneity between your threads. If all of your threads are similar in terms of their characteristics, then you don't have much choice, right? It doesn't matter what you schedule together because they're all similar. The interference patterns will all be similar. So heterogeneity in threads is very important here. Okay, let me summarize what we've covered in the last few lectures. Basically, we've talked about 4 fundamental interference control techniques. The best is really to combine them all. I'm not going to answer this question, but how would you do that is an open question actually. How do you combine all of these techniques? Prioritization, data mapping, core source throttling, application thread scheduling. Anybody has any guesses? It's not easy actually. Even a single technique itself is not easy, as we've discussed. But combining all of them together is not so easy also. But it's done in existing systems in some way. It's all basically heuristic. Sometimes the techniques are coordinated well with each other. Sometimes they're not. They contradict each other. As long as the system somewhat works, people are okay with it. And usually the way they find out that something doesn't work is they get a huge slowdown in some workload that they care about at some point, and they go and try to fix the technique. But maybe there should be a more principled approach to fix this problem. It's not clear. That's where research can contribute a lot, but it's not an easy problem also, because it has many dimensions actually. Ideally, again, this is where you really want artificial intelligence, I think, because you really want your system to be self-controlling, but it's very difficult, I think. Okay, so we basically covered 2 different types of approaches: smart versus dumb resources. Smart resources example is quality of service over memory scheduling. We didn't cover quality of service over caches or interference over caches. That's what we're going to do next, or efficient caches. But it's different from the dumb resource approach, where you don't touch the resources. Source throttling, channel partitioning are examples, thread scheduling. And both approaches are actually effective in reducing interference. There's a lot of evidence for this in research and in real life. And there's no single best approach for all workloads. There's also a lot of evidence for this in research and real life. There's no single best approach to quality of service and interference control. So you need to combine them somehow. And we covered 3 fundamental techniques. Actually, it's 4, I think. Scheduling, prioritization, but I think I combined scheduling in different ways. Request scheduling and thread scheduling. They're actually different things, but they're scheduling approaches at very different granularities. Source throttling and memory partitioning. And all approaches are, again, effective in reducing interference. There's a lot of evidence in the field for this. They can be applied at different levels, hardware versus software. Actually, pretty much everything that you can do in software, you can do in hardware. That's clear. The opposite is also true, as long as you put the right interfaces, such that the software can actually control what's going on in hardware. And there's no single best technique for all workloads, which means that you somehow want to combine, and combined approaches and techniques are actually the most powerful. And there are some examples of this. This is a relatively old example, as we've discussed. This integrated memory channel partitioning and scheduling, for example. By combining both of them, you get a better performance and better fairness than using either alone. Okay, so a little bit higher level summary. Basically, we started with quality of service unaware memory, and we got an uncontrollable and unpredictable system. And we wanted to fix that problem. We wanted to provide quality of service awareness, and we did that. This improves performance, predictability, fairness, and utilization of the memory system and the entire system as well. And we discussed many new techniques to minimize memory interference, provide predictable performance. Is this enough? It's not enough. There's a lot more to do actually in this area. There are many new research ideas needed for integrated techniques, and also closing the interaction with the software. How does the software have a lot of control on these techniques? And also, how do we actually make sense out of these techniques? I think it's not very easy, as I said. There's another place I think where machine learning can help a lot. But again, you need to figure out the right techniques. What did we not cover, which we may cover? There's a lot more actually over here. The problem is actually much more complex. One is prefetches, for example. We didn't talk about prefetches. We assume that all requests are demand requests. But what if some requests are requests that are sent by the prefetcher? And there are many such requests actually. Existing systems do very aggressive prefetching to hide the memory latencies. So many requests are prefetch requests. But prefetch request is fundamentally different from a demand request. You may not need the prefetch request right away, but that's not always true. Sometimes a prefetch is late and you need that prefetch request. It's as important as a demand actually, because if you delay it, you're going to stall anyway, right? So that's the idea. So how do you do that? Actually, there are some works related to that. I referenced them somewhere earlier. if you're interested, we can talk about it and you can read about it. So the key idea is you want to understand your prefetches. If your prefetches are accurate, then they're almost as good as a demand, actually. You can treat them similarly to a demand. If your prefetches are not accurate in general, you may actually want to think about dropping them. And if you can classify your prefetches this way, maybe not necessarily black or white, or with shades of gray, like somewhat accurate. I'm not sure if it's fully accurate, but it's likely inaccurate. Then you can actually do very interesting things. So basically what doesn't work is always prioritizing prefetches the same as demands. That fixed policy doesn't work very well. And also always prioritizing your demands as a higher priority than prefetches, that also doesn't work very well. So now this opens up other questions, of course. If you have prefetches, how do you estimate the slowdown of an application in the presence of all of these prefetches? It becomes really interesting. So it actually, this is, if you have prefetches, techniques like stall time fair memory scheduling break down even more, whereas techniques like what we've discussed, the memory-induced, interference-induced slowdown estimation work better because they are based on request service rates as opposed to counting interference on different requests. Okay, there's more here. DRAM controller co-design. I don't know what this means. That should be really more like controller cache co-design. We should fix that. So basically, how do you have memory controller and you have the cache, how do you coordinate them in some way? And we didn't talk about that. We're going to talk about cache management in a little bit in the next lecture, so I'm going to not talk about this as much. But you could actually co-design the DRAM controller and the cache. For example, I'll give you one example that's actually being employed going forward in the systems slightly, depending on which kind of system. But if you actually know which rows are open in your DRAM, you could decide to take advantage of those open rows by removing the dirty cache blocks from your last level cache. If your dirty cache blocks go to the same row that's open in your DRAM, and you're doing already writes to the DRAM, why don't you schedule those dirty cache blocks and evict them from your cache? This idea was proposed. There are different implementations of it. And it actually improves your performance significantly because you're taking advantage of the row buffer. There's already an open row buffer. Just use it. Of course, you need to be careful because you don't want to delay other requests while doing that. Cache interference, we're going to talk about interconnect. We're going to talk about also write-read scheduling. That's something we didn't talk about. Actually, it's even more complicated because there's not just prefetches. There are writes and reads. And as we know, in DRAM, when you're doing scheduling, you need to switch between write mode and read mode. That's fundamental to many memory technologies. So that actually affects the interference as well. Now a write-intensive application can deny service to read-intensive applications, potentially, right? So how do you handle that? We didn't talk about that. And how do you design the DRAM itself to reduce interference? I'll give you an example paper on this, but I'm not going to talk about that in detail since we don't have a lot of time. And also interference issues in near memory or processing in memory. So if you have processing in memory engines, accelerators, how do you handle interference in that accelerator? You may actually have many cores that are requesting some things from the processing in memory engine. And there are a lot more, as you might imagine, over here. Okay, so what the future might bring, this is just some examples. I think we need more techniques, for sure. More simpler, as much as possible, simpler techniques, yet powerful techniques that can control interference and that can do scheduling. Memory and plus interconnect is another example, actually. We want real implementations and investigations. I think this is where some of the infrastructures that we discussed earlier could be very helpful. Actually, SoftMC that we discussed for DRAM testing has a lot of capability for testing these memory request scheduling mechanisms on the FPGAs. And of course, interference and quality of service in the presence of even more heterogeneity. Right? We talked about having many accelerators, but PIM, processing in memory, is another accelerator. And it sits somewhere else. It sits close to memory. So it requires interference and quality of service control mechanisms also. And how do you do that becomes interesting. And certainly automated techniques for resource management, like everything else we discussed, can we make it automated, is important. Okay, so I'll put this picture over here. Maybe this will give ideas to people. Like actually studying these in an FPGA becomes very interesting, I think, because you have a lot more control in changing the memory scheduler in an FPGA. And you can actually emulate a lot of the things that we've discussed. But you know about this already. Any questions? Comments? Am I going too fast? I guess not. Okay, so this is, we're going to take a break in a little bit. I'm not going to cover the some other ideas part, but this is actually one example of using DRAM, changing the DRAM to actually reduce the interference. But I don't think we have time. I want to cover the caches, but I'll leave this with you. Basically, this paper tackles the problem of interference between processor and I/O devices, something we didn't really tackle. They both go through the main memory, and they communicate through the main memory. I/O device do I/O access, processor does CPU access, and main memory is an intermediate layer between them, basically. Physically, the way this is done is this way today. I/O devices, when they want to access main memory, put something into the main memory. Think about a storage, SSD, for example. If you want to pull some data from an SSD into main memory, what happens is you bring the data through the memory controller into the main memory. While you're doing that, the memory controller is also servicing requests from the CPUs, right? So you have an interference between the CPU requests and the I/O device requests. That's true for a GPU over here. That's true for a network device. That's true for many, many other things. Basically, any other I/O device over here. So you have interference between I/O and CPU access. And also you have high contention in the memory channel over here. And also you have high ping cost in the processor as well, which we're not going to go into that. The key idea, I'll give you the key idea of this work. The key idea is this, basically. Why don't you have another port to main memory, maybe with little cost, such that the I/O devices can use that port and do not disturb what's going on in the processor. So you basically decouple the I/O access from the CPU accesses and isolate these channels from each other. As a result, you get many benefits. If you read the paper, you will see the benefits. Actually, maybe I'll cover this executive summary and then we'll be done. Basically, the approach is you design a new DRAM architecture with two independent data ports. It's called dual data port DRAM. Of course, you don't want to increase all of the ports to all of the banks. So this paper has a simple design that adds some area cost to DRAM, but it's not huge. And you connect one port to the CPU and the other port to the I/O devices. That decouples the CPU and I/O accesses, and this paper shows multiple applications of this. Basically, you can enable better communication between compute units, CPU and the GPU. You can actually go through the memory directly without going through the memory controller. And you can do in-memory communication, actually bulk in-memory copy and initialization much better, and also memory and storage communication, page fault. Whenever you get a page fault, you need to bring the data into memory. You can put it directly into the memory as opposed to going through the CPU. And you can do prefetches, of course. And the result is significant. You get significant performance improvements if you actually do this. You can read the paper for more detail. And actually, this paper, I think, scratches the surface because you cannot evaluate all of these very easily in simulation. And you have to do this in simulation because there is no DRAM that provides these multiple data ports. There are some expensive DRAMs, actually, that does do that, but it's not easy to modify and get. And you also get CPU pin count reduction in this case because now you don't need to have I/O devices accessing the CPU chip. Those can directly get connected to the DRAM chip. But if you really want to know more, I'll leave the slides inside there so you can take a look at them. Yes?
So you mentioned that there could be processing elements over there as I/O devices, right? Like GPUs or something?
Mm-hmm.
And if they could directly access the memory through other boards, how do you keep these two like informed of the other ones? Like, how do you manage the coherence?
Yeah, that's a completely different question. Yes, you need to manage the coherence somehow. Yeah, and you can read the paper for some detail on that. But that's very similar to how you do that. How you do it in a distributed system today, right? If you want to have coherence in a distributed system, you need to manage it. It's the same thing, basically. But read the paper if you're interested. That's a good question. Okay, what else? Or do you want to cover this idea? No, I think we should take a break, and you can look at the slides on your own.